Okay, I have started the recording, and before we continue with today's session on the tour of OCaml, I just want to update you on a couple of logistics. The first thing, of course, is the part 1 of the tour of OCaml is available on my YouTube channel, so you can actually go and watch it there if you have not watched it already. And the notes from the part 1 session are also available on my GitHub account on a Twitch repo, including today's session, so you can actually refer to it while you go through the sessions. So in the first session on the tour of OCaml, when I used the OCaml playground, it was not mobile ready yet, and so I would like to acknowledge here the work of Fatuma, who actually created a PR to get that mobile responsiveness here. And so this now allows you to use the playground on your mobile or your tablet, and it's quite responsive as well. So whether you are watching this stream or video while you're commuting or on a different device, you will be able to use this interface, which is kind of nice. So I like to acknowledge this contribution, and with that, let's get started on today's tour of OCaml part 2. So quick recap, we went through basic expressions, syntax, semantics of the OCaml language. We went through basic data types, and then we continued down the path to learning about expressions, functions, and then we proceeded to look at anonymous functions, recursive functions. So I would encourage you to try it in the ocaml.org/playground, and so we looked at partial applications, higher order functions, the unit type, and we stopped at data and typing, which is where we will resume from today. Okay. So let's continue and learn about type conversion and type inference next. So I'm just going to try these examples on ocaml.org/play, which is there on the right side of the screen. So I'm just going to clear this output here. I'm going to clear all the contents on the editor, and we will go through these examples. So as we already know, OCaml, everything is a value, and values have types. So here if I do like 2.0 plus, right, dot 2.0, I'll have to use the plus and dot to indicate that I'm doing a floating point operation. Right. Now suppose if I tried something like 1 is an integer and I add 2.5, which is a float, and the plus operation is exclusively for integer, right? So if I run this again, the compiler will throw an error saying that this expression has type float, but an expression was expected of type int, which is exactly 1, right? I can also not do 1 plus dot, right, and try to run it again. Again, it'll complain that we're trying to add a int and a float together, right? So the way to handle this is to use the float of int function to explicitly do the type conversion. So I say float of int of 1, which is an integer, convert to a float, then I do the plus dot for the float operation, and then add 2.5, and then I run it again, and we get the result of 3.5. So type conversion is explicit. We briefly looked at lists. So we know that this is a empty list, right? And we can have a list of integers, for example, or we can have a list of Boolean values, right? Or we can have nested lists, right? So this is a list of integers. So I am actually typing each expression. So when you are practicing, I would like you to type each expression so you actually understand the syntax. Let's run this again. So you have the results on the output. We have seen prepending to a list. So we use the cons operator here, and again they're all integers, so you get a integer list of 1, 2, 3, 4. So we can have a list of integers, a list of bools, a list of strings, and so on. Okay. We can do pattern matching on these lists of integers. So earlier we have seen an example of using an if-else condition, but here let's write the sum function if you want to sum a list of integers. So we use let keyword and then rec for a recursive function, sum u, and we're going to match u with its empty list. I'm just going to return 0, or I take the head and the tail, just add the head of the list, and again I call the recursive function sum with the tail of the list. Okay. Let's check that this definition is correct. It looks fine. Then I can call the sum function with a list, and this should basically return me the sum of 1 plus 4 plus 3 plus 2 plus 5. Right, so this is a sum function on integer list. But you can have polymorphic functions on list, right? So which means in the next example we are trying to find the length of a list, but the list can be of either integer type or it can be a string type and so on. So let's try that example here. So let's define this function length, which is a recursive function, and we are matching the list. For an empty list, we just return 0, and I don't care what the first head of the element is. I just count it as one element plus, and I call the length function with the tail of the list, right? Let's check if the definition is correct. That looks fine. Now I can call the length function on a list of integers, or I can call it on a list of strings. Okay. And it should give me the corresponding length of the list, right? Also, you can do nested lists. So in this case, I have one list, and hence it returns integer as 1, right? So So you can use polymorphic functions on lists. We have seen higher order functions, and we can apply the same pattern matching here as well. So let's try this example with the square function. So we have used this earlier. Let square is x into x. We are just multiplying the input with itself. So we'll make sure that it is fine, that it looks good. Now we are defining a new recursive map function. So we have a recursive map which takes a function and a list, and then we do the pattern matching on the list. If it's empty, I'm just going to return empty list, and then we take the first element and the rest of the list and apply the function to the first element of the list by forming a new list, and then I call the recursive map function with the tail of the list. Right. Let's check if this definition is fine. That looks good. Now I can apply or call the map function with the square function. So basically you can pass functions to functions, to higher order functions. And let's say I'm giving an example here of an integer list, and this should give us the results of 1, 4, 9, 16, where we are applying the square function to each and every element in the list. So it's simple, it's elegant, it's easy to read, and pattern matching is great. Right. Now, moving along, the topic of polymorphic functions and higher order functions, I want to show the example of the option type in the standard library. Of course, here we are only giving you a quick tour of the OCaml syntax, and in later sessions we will go deep dive in the respective modules as well. Right, so I can do show option here, which should give me the definition here. So it's either none. So this none and some are called constructors. So it can be either none or it can be some of a type, right? So let's define f, which takes an option. We are doing pattern matching here, and so we have to pattern match for all the cases. So here I'm saying if it's none, just return none. If it's sum of none, I just return none. And if the sum of x, then I just return sum of x. Let's make sure we have not made any typos and the syntax is good. Right. So we had earlier used if then else, but pattern matching, it looks good to read, maintain, manage, and it's just beautiful OCaml. So this is the classic example. Earlier I talked about how we can handle multiple cases with if then else, and g of x uses the if else, but g dash uses the pattern matching. So let's try that as well. So let g of x is equal to, so coming from other programming paradigms, you might be tempted to use if then else constructs, but let's try to use as much of pattern matching when we write OCaml applications. And then we have the else clause, and let's just check if we've not made any typos. That looks good. but then again we write it with the pattern matching case. So foo is 1, we match for bar, we return 2, match for bars, we return 3, and return 4, and the all match case I just return 0. Let's check that definition is good, that looks fine. Okay. Now, of course, when we write some of these pattern matching cases, OCaml does hint you if it doesn't match some of the cases that are not exhaustive, as in this example, right? So, they're using OCaml play, or you are using any editor, you will have these helpful functions to help you with the syntax. Alrighty, moving along, let's look at pairs and tuples. So we have seen lists. So now we look at tuples or tuples, how you call it. So here we have a tuple with integer, a string, and a character, right? That's how you define it, right? So it's int, string, character, and or we can have a list and a Boolean value. That looks fine. Okay, and of course you can access these components of a tuple. So this is a second function where you want to match the second element in the tuple. So again we go for pattern matching, match p with, I'm not interested in the first element. If the second element, I just return pattern match and return the second element. Let's check if the syntax is good. That looks fine, and then I can just call the second function with a tuple, say integer and a string, and it should basically return apple string for me. That looks good. Continuing, we now going to look at enumerated and union data types. So here we have a type called primary color, and this is how you define using the type keyword. And as I said earlier, these are individual constructors. Let's check the definition. That looks good. So now I can create a list of primary colors. So I just say red, blue, red, for example. There's a typo here. Yeah. And that's a list of primary colors. So that's how we define enumerated data types. And then we can go on to union types. So in this example here we have HTTP response is a data of string, or it can be an error code of integer. So it can be the string or integer. Let's define that type. Looks fine. And then I can define a HTTP response here. Just going to copy this for this example. Right, that's a data of string, or I can have a error code of integer type, right? So that will pass as a HTTP response type. Nice. So these are good examples of enumerated types and union data types. We can also do pattern matching on these variants. So this is an example of a, let's say, a page range type. We define it as all or current, or it's a range of integer and integer. Sure that passes, that looks good. And then we can do pattern matching on this. Let's define the color to RGB. You pass a color and then you match the color with, if it is red, you say 0xFF 00, if it is green 00xFF 0, and if it is blue 000xFF. Yeah, I can align this a bit. The definition looks good. Similarly, we can define the HTTP status code response. So we pattern match on response with data. I'm not interested in the argument, I just return 200, and if there is a error code, I just return the code. Right. Let's check the definition is good, and then we can sort of use this is printable function for the page count current range. Again, we match for the range. So here we are matching for the page range constructors, all current and range. So we need a entry for each of those. So if it is all, I should return true. For current, I have a conditional check. If it is, the current is, if 0 is less than or equal to current and current is less than page count. And then for range, it's a tuple of int and int, so I have low comma high, and then I again have a conditional check to check for the range of low is less than or equal to high, and high is less than page count. Hopefully I've not made any typos. I check run and that looks good. Right, so you can do this pattern matching on these types. Let's look at records next. So you can pack several elements of several types into records. You can basically have a name for each of those attributes. For example, for a type person, I can have a first name string, a surname is also a string, and then an age which is int. So I don't use a semicolon in the last field, right? I'll use it for the first name and surname. Let's check that, that looks fine. So I can create a new person, Shira, say first name, surname, and age is 76, right? So we have Shira is a type of a person and who has specific first name, surname, and age. Let's use these types and also do pattern matching on these types. So we have create less is equal to say dot surname. So this should return Hui, okay, and we can define a new function to check for if the person is a teenager. So you match for the person, and in this case we only are interested in the age attribute, so you take the age, not interested in the other record attributes, and you do a check for x is between 13 and 19 in this case. Let's run this again, and that's good. Now we can check if Jira is a teenager, which is not, so it says false, right? So that's how you sort of build types and write functions and then use those functions. And slowly we will look into more modules, but I'm just trying to give you the quick essence of the OCaml syntax. Now coming to the error handling, we do have exceptions. So for example, if we do 10 divided by 0, for example, we will get an exception division by 0. And if you want, you can actually also raise the exceptions using the raise function. So in this example here, I check if n is not 42, then I say I call failure with a string, else I just return the integer, right? And I can check ID 42 or 42, which it should return 42, which is the success case. And if I do say 43, for example, it should return me the failure string exception. Okay, it's quite simple. You can also use the result type. So like the show option, I'm going to see the definition here. So it can either be OK, the first constructor OK of A type, or it can be error of B type, right? So that's the type of result. So I can have something like ID 42 result. If n is not 42, then error sorry, else I can say OK of n. Right, and then I can use this to check for 42, and I can use it to check for 0, for example. And of course we get OK for 42 and error for the 0 value. And of course you can do pattern matching again, which is nice. You can say OK of n, I just return n. If it's an error, I just return 0. So in this case for 0, it's going to just return me 0. Okay, so pattern matching is cool. OCaml does support imperative programming, so you can do variable definition and you can mutate variables. Ideally, we would like to use immutable approaches, but I just give you an example here just for to demonstrate this use case here. So let me clear this. So here we use the let syntax, and I say let r equal to ref 0, which means the contents of r is 0. So if I want to get the value of r, I can do the bang symbol and r, and it should give me 0. I can imperatively change it with colon equal to say 42. So I am explicitly changing the value of that. And then if I again ask for the value, it should return 42 in the second case, right? Of course, you can do for the string manipulation and so on. So this sort of gives the high-level overview of the syntax and semantics of OCaml. This is the show option, which gives you all the other functions that are available. And we've already seen list functions. Similarly, the option has other functions that you can use. So we are reaching the 30-minute mark. So what I'm going to do is stop here, and I will make the recording available on YouTube, and the notes are also available on the GitHub Twitch repo, so you can refer to the notes. And what I would like you to do is have a similar setup, go to the Tour of OCaml page, keep it on the left side of the screen, open OCaml.org play, watch both the videos on the Tour of OCaml. I want you to type all of the syntax and evaluate the expressions on the playground. And once you're familiar with this, we will next move on to do a more deep dive into each one of those modules. We look at data structures and all of that. So I definitely want to do more hands-on sessions. I will try to keep it short for 30-minute sessions. Once I complete few more sessions, I will definitely have chat Q&A sessions, so it will be more interactive as well. So we'll try to mix and match between lecture type sessions as well as Q&A sessions, so it's quite interactive as well. So I said we like homework, so please open the Twitch repo here. I have pushed the changes for all the examples that I have tried. So do the hands-on, don't copy paste the syntax, type it yourself so you better understand what each syntax is and how to use it in the playground. And I will make the part 2 recording also available on my YouTube channel. Thank you for joining, and we will see you again next Thursday. Ciao.